I'm trying to switch off the camera, so only audio, and let's start the screen sharing. So the same classes continue yesterday classes. Okay, so up to this point we have finished yesterday, and from today, so we'll start this thing, most successor first. The same problem, but we'll try to solve using different approach. And most successor first is actually another heuristic. It is not proved to be give any approximations, but this is algorithm. Okay, so set up a priority list L by non-decreasing order of job successor numbers, and execute the list policy based on the priority list L. So this is set up a priority list based on this most successor first, and then execute the list seedling policies. Okay, how this MSF works. So SAM earlier, whatever we have take an example for SAM graph with SAM number processor, how it looks like. So which job have highest priority because most successor first? Can someone say? Hello?
Sir, J8.
J8? Not J8. J13 have highest. J8 have most immediate successor.
Okay.
So J8 have most immediate successor, but whenever I say most successor first, then clearly this J1, J2 up to J7, they don't have successor. Then J9 have one successor. Then J10, 11, and 12 have two successor. J8 have 6, and J7 have J13 have 7 successor. Are you able to see the screen? Yeah. So
Yes.
which task get first scheduled? We'll take first J13. Okay. So this is the list. So if you look at the group, J13 get 7, J8 got 6, and J12, 11, and 10 they got priority 2, and J9 got 1, and then J7, J6 up to J1 they got all 0. So they are least priority. First priority is J7, J13. So J13, J11, and 12. So because J8 you cannot schedule because J8 have actually dependency on J13. So we cannot schedule J8 and J13 at the same time. So we need to maintain the dependency and then schedule priority. So higher priority tasks may not actually what I can say be ready. We will look at priority also readiness. Okay. So this is the way we'll schedule. So this is most successful part, and MSF is just a heuristics. So there is no proof of approximation bound or anything. Okay. And if you look at whatever you solved problem was actually this previous case example case, what problem we solved? We solved this problem. So the problem is this one, PM, president constant, then PJ is equal to 1 and Cmax. So now we'll move towards another problem, that is PM, no precedence constant, but PJ is arbitrary, and we'll try to minimize the Cmax. So the problem we're trying to solve is what is the problem? PM, PJ, and CMAX. What is the meaning of the problem? Given the processing time of n jobs, P1, P2 up to Pn. So that means an integer m. M is number of processor. Okay, so in this case, m processor, identical processor, all tasks arrived at time 0. Preemption is not allowed, no deadline business. Okay, and we want to minimize the overall execution time. And this is the common problem. So n taxes, m processor, we want to schedule n taxes onto m processor so that overall execution time is minimized. So that the completion time, also called the max one, is minimized. This is the most common problem. We'll see. Okay, and can you say, suppose we map this problem to 0-1 linear programming solutions. Okay, 0-1 linear programming solutions for the scheduling problem. So how we'll define this thing? Suppose let's consider a variables. Okay, so binary variables xij, which is from 0 and 1. So this is binary variables. Whether job j is scheduled in machine I. Okay, so xij means, okay, whether job j is scheduled on machine I or on machine I job j is scheduled. Okay, so xij is equal to 1 if job j is scheduled on machine I. And this is another things what we're trying to do. So summation of x, this is summation of xij from I is equal to 1 to m and equal to 1 for each job j. For each job, this summation is 1. So we know this xij is binary. Xij is binary, either 0 or 1. And whenever I say for all the machines for a particular job, xij is equal to 1. That means each job is scheduled to only one machines. It says each job is scheduled to only one machines. And each machine can finish its job by time t. Suppose what we're trying to do, and now we're trying to put a constant. So we want to find out the Cmax time, and we assume suppose the Cmax is t. Okay, for each machines, so j from 1 to n. Okay, so this is for job. Okay, and xij and pij. What is xij? If jth job is assigned to ith machines, that means ith machine have jth job, then this will be 1, otherwise it will be 0. Okay, and this is processing time, pig. So in all the cases, what I are saying is this is not what I can say. If it is machine are identical, so this is what again, pj also more than enough. So in this case, simple pj is also, it is more than enough. Okay, we don't require pij, we require only pj. And what another thing is, xij is always greater than or equal to 0. So it is binary. Again, this thing is for each job, for each machines. Anyhow, because these things are and whenever you solve linear programming solutions, so we can use any linear programming solver. So what kind of linear programming solver have you heard of? Have you heard about linear programming thing in your
Yes,
earlier
sir.
courses? What kind of linear programming solver have you heard of?
Sir, simplex method.
Simplex method. Any other tools have you used? Suppose you want to solve any problem using linear programming, and suppose you want to use some tool, just like MATLAB or LP solve or Simplex. So there are many linear programming tools are there. Give you a problem and it will give you the solutions, but it might take exponential term. So LP underscore solve. Okay, this is Linux tool. Simplex. This is IBM tool. Okay, in MATLAB also we have some linear programming solver. Okay, and in GNU scientific library also we have linear programming solver. GNU asleep, scientific library. Many places we have linear programming solver, and you can use, suppose you formulate the scheduling problem onto a what I can say linear programming problem. Here 0, 1 linear programming. So we can call this as JOLP. Okay, JOLP. Okay, 0, 1 linear programming, because this is 0, 1. Otherwise, if it is integer, then I can say ILP. Okay, if it is integer, then I can say integer linear programming. If it is a 0, 1, then it is a 0, 1 linear programming, JOLP. Otherwise, by default, we say it is simple linear programming. And most of the linear programming tool, they solve means ILP, also they solve JOLP also. Okay, so but most of the times this problem solutions, it takes exponential time. And if you give our older problem, so and what we want to minimize? Minimize is t. So we want to minimize the overall execution time t. So this is this problem we have made to 0, 1 linear programming, JOLP solutions. JOLP solution for the same scheduling problem. For the scheduling problem PM, PJ, and CMAX. For this problem, we formulated the problem into a JOLP problem, and now this problem can be solved using any simplex solver or LP solver, MATLAB linear programming solver. This will give you optimal result because you are formulated into linear programming. Okay, it may take exponential time to solve, but it will give you the optimal result. Any doubt? Okay, so now we looked at because this ILP, GLP solutions, it may take it takes optimal, it give optimal result, but it takes a huge amount of time. Particularly, it is not solvable in linear time. Okay, linear or polynomial time. So it takes exponential time. So in general, we go for heuristics or approximations. So there is a very good approximation called least scheduling for the same problem, minimum expansion scheduling. So what problem we are solving? PM, PJ, and CMAX. So we have M identical processor, arbitrary execution time, no preemption is allowed, and we want to optimize CMAX. This is common problem. So basically, this is standard problem whatever is looking. So how we can solve? So we can solve using list scheduling approach. It is an approximations, and this list scheduling algorithm, what you do, it order the job arbitrarily. So basic list scheduling approach, it order the job arbitrarily and select or schedule the jobs on machines in this order. So whatever the order, arbitrary order, and schedule the next job on the machine that has been assigned to the least amount of work so far. So what is the scheduling it does? It take a job and whichever is least loaded machines, just put it there. So take a job, it order the job arbitrarily. So no ordering defined. Okay, take the job arbitrarily, and one after another, it take a job, simply schedule to the machines which have actually a least amount of work assigned so far. So this is a least loaded one. And till all the job got assigned, so this process repeats. So this is very simple one. So how it do? Let's see with animations. Suppose in this case, examples, how many taxes we have? A, B, C, D, E, F, G, H, I, J. So 5 plus 2 plus 3. So, 10 taxes. And we have 3 machines, machine 1, machine 2, and machine 3. So, yeah.
Sir, I think we are still seeing the previous slide in which the algorithm is given. Yes,
yeah.
now we can see. Now we can see.
Okay, so there are 10 taxes. Okay, and so we're taking A and assign to first machines, machine 1. Then we're taking B, assigning to machine 2. Okay, and now if we look at C, so where will definitely assign? Which machine will assign? for C. C will go to third machines. Okay, because C is machine 3 is not loaded. Now, if you look at next access is D. So where I should allocate based on list ruling?
Machine 2.
Machine 2. So B means it's actually, if you look at this thing is very lightly loaded, this one. So we'll assign here. Okay. Then among machine 1 and 3, so whichever is lightly loaded, we'll assign there. E. Whichever is slightly loaded, we'll assign there. Then next, so we'll assign F will be assigned to machine 3. Okay. And G will be assigned to which machines? Now machine 2 is lightly loaded. Machine 2 is lightly loaded. Now next is.
So what if all the machines are equally loaded?
Look
What if all the machines are equally loaded?
Equally loaded. Now, how much work we have put into the machines? So because initially all the machines are free and we are trying to allocate.
Okay.
We are allocating. Not that machines are already loaded. We are allocating. Is got my point?
So what if all the machines are equally loaded?
I'm not getting your questions. What if
So
all the machines are equally loaded?
Let us say at some point of time, all the machines are equally loaded.
Then
and
if
we have to schedule.
Choose arbitrarily.
Okay.
In that case, that's fine. In that case, choose arbitrarily. So next is H you are, because machine 1 is lightly loaded. Then you are going for this one. Okay, again machine 1. And next is this machine is lightly loaded. So next is this machine is lightly loaded. Then I will put into this machines. Okay, so now what is the CMAX in this case? This is the CMAX. This is the CMAX. So overall execution time on 3 machines, this 10 taxes is this much. And this is one approach. Okay, this is one load balancing approach. Okay, list ruling load balancing approach. So how far this is from optimal, or whether this heuristic can be proved that it is a approximations. So if you look at, so for this 3 taxes, okay, this is 3 machine and 10 taxes. This is the optimal. This one is optimal. So let me draw this. This one is optimal, and we are going up to this. So clearly, you can say that this is not optimal. But can we prove somehow that it is how much far from optimal? So let's say this LS is 2 approximations. So can you prove, or can you say that thing? So let's try to prove this list ruling is 2 approximations, arbitrary list. What we are saying is order the task arbitrarily. Okay, then let's try. So basic idea is a list of job. Schedule the next one to as soon as machine is free. So this is the idea. And suppose this is the green case. What is the current load? And there are 2 taxes E and F are there. Okay, and in this case E is leastly loaded, so that's why we are putting E here. And for the next guy, so C is lightly loaded, and we are putting, what we are putting is F we are putting in this case in the machine. In this case, machine 1, 2, 3, 4. So machine 3 is slightly loaded. So that's how we are putting the F here. So suppose F is the last taxes and E is the last but one. Okay, and in this case, so A is the what is? A is the our CMAX. Whatever the getting CMAX based on the list scheduling approximations. Okay, so this is the CMAX. A is the CMAX produced by a list scheduling algorithm. A is the CMAX produced by the list scheduling algorithm. Job F finishes last at time A. So A is the CMAX time produced by the list scheduling algorithm. Okay, so can I say that whatever the optimal, suppose A opt is there. Okay, so suppose A opt. Okay, suppose opt is there. So any optimal algorithm, can it produce the, what you can say, optimal Cmax below this point, less than C? Can it be less than S? Because up to S, all the machines are BG. Definitely opt will be always greater than equal to S. Can I say this thing?
Yes, sir.
Yes.
Because it cannot be lower than that, because all machines are BG up to time S. This is correct. Okay, so another thing is opt. Okay, so this opt is greater than value f. So this value, can I say opt will be definitely greater than f. So execution time of these tasks, it cannot be lower than execution time of any of the tasks. Opt is greater than s, I can say greater than equal to s, and opt is greater than equal to f also. So what is f? F is actually f is task with execution time value is f, and this f is equal to, if you look at opt is greater than equal to this, means what is the value of f? F is equal to a minus s. F is equal to a minus s. So what I'm trying to see is, so f must be scheduled at best scheduled at some time. F is equal to opt to be definitely greater than equal to f. F must be less than equal to opt. And another thing is a minus s is less than equal to opt. And another thing is s is equal to s is equal to also less than opt. Because whatever the opt is optimal algorithm it will produce, it will be definitely greater than s, greater than equal to s. S is less than equal to opt. Okay. So if you look at, if you put together, so a is equal to a minus s plus s, and what we are trying to do, a minus s and s, and a minus s we are getting from here, and s we are getting from here. So a minus s we are getting from here, and s we are getting from here, and if you add these things, it will be definitely a will be less than 2 opt. Is this clear? Very simplistic method.
So, so sir, we are assuming that A, B, C, D, all four of them were optimally scheduled.
Which one? ABCD? Our not optimally, whether optimally scheduled or not, this list scheduling will anyhow it will schedule to the list loaded machines, and up to this point S, all the machines will be busy. Up to this point, all the machines, machine 1, 2, 3, and 4, all will be busy. They have work. That means it says that optimal value of this Cmax cannot be less than S.
Yes, sir.
So whatever way is scheduled, whether optimal schedule or not scheduled, but it cannot be less than S. Optimal will be more than S. In that way, I'm saying. Because in list scheduling, up to this point, they are all are busy. All machines are busy. Any scheduler if you do, or any optimal scheduler also do, it will be busy up to S, time S. All machine will be busy up to time S. Otherwise, it cannot produce optimally. Is this fine? Okay, this is very simplistic, what I can say, argument. And with this very simplistic argument, we can prove that whatever optimal means least seedling algorithm produce result, this Cmax will be 2 approximations. It will be less than 2 opt. And this is very old 1966 algorithm. Okay, so and what we can prove that it is actually 2 minus 1 by m approximations. Earlier it was 2. Earlier it was 2, and now it is reduced to 2 minus 1 by m. So it is also significant. Suppose you are doing for 3 processor, then what will happen? Suppose 3 processor, 2 minus 1 by 3. What is 1 by 3? 1 by 3 is 0.33. So it is 1.66, and 2 and 1.66 have significant difference, because whenever you are doing approximations, so if you are going for a lower one, then actually it is better. Okay, so 2 minus 1 m approximation is there. So then we can do a little bit more analysis, and we can prove that this is actually 2 minus 1 by m approximations. So what we are trying to do is same argument. So we are trying to say let t is equal to summation of ti. So all the execution time of taxes. And what we are doing is, suppose this is k is the last access in list scheduling. K is the last access in the list scheduling. Then up to this point, all will be busy. The same argument. And suppose A is the Cmax time produced by the list scheduling algorithm. The same argument we are trying to do. So this total t minus k. So this is t minus k. T is summation of all the taxes, execution time of all the taxes, will be greater than m into a minus tk. What is a minus tk? This is a minus tk. Up to this point, all machine will be busy. What we are saying, nothing else. Up to this point, all machine will be busy. And we're rearranging this thing, and nothing else. A is equal to, what is this? A is equal to, this is t by m. So what we are trying to do is t minus tk equal to, greater than equal to m into a minus tk. This is up to this point, all machine will be busy. And what I'm trying to say is t minus tk is greater than equal to m into a minus tk, because you are getting a, means what I can say, multiplication factor of m. We are getting a multiplication factor of m. Okay. Another thing is m into t star. If you look at m into t star, it's greater than equal to t. What is it? If you look at any optimal algorithm produced, any optimal algorithm it will produce. Okay. So definitely t star will be greater than equal to t by m. So what is t? In this case, t is A is optimal result produced, a result produced by list algorithm, and t is summation of this thing. That means t star is let me rewrite. T star is greater than equal to summation of ti by m. Can I say this thing? T star means Cmax time produced by any optimal algorithm will be greater than summation of all execution time by m. In this way, if you do this thing, then this summation of ti is t, and t star is greater than equal to t by m. Okay. And another thing is t star is always greater than, for every taxes, t star is greater than equal to tk. So for every taxes k, that also is there. If you look at both the two conditions, then we can come up with these things. Suppose what is a? A. So can I write a is equal to t by m? Okay. So this thing. So whatever this thing is written, from this equation we are trying to get a. Okay. So a is less than equal to t by m plus tk m minus 1 by m. Okay, and then we are replacing. So this is t star, and in this case TK. There is another thing is called TK. Okay, this TK. From this we are getting another T star. And in this way, we can prove that A is less than equal to 2 minus 1 by M T star. So a little bit more analysis, but more, or can say, reduced approximation value. Is this clear?
Yes, sir.
Same argument. It is same argument. There is no different argument. Same argument. This is the same argument what we put in. Okay. So what are the worst case can be in list ruling? General list ruling.
Sir, the
Suppose,
last task schedule is longer.
Last task is bigger taxes. Suppose last taxes is bigger tax, then that is the worst case. Suppose M taxes and you are having M processor and M plus 1 taxes comes as a very big one. So in that case, last tax need to execute for a longer period. That is the worst case. So how to do? So how to handle this thing? So the best rule is LPT rule. So list with longest processing time. So list scheduling can do badly. So whatever the worst case, whatever you have seen. So list scheduling can do badly if long taxes at the end. That is the worst case, and it spoil an even division of the processing time if it is longer tasks are putting into towards end. So now we assume that jobs are given ahead of time, then LPT rule works very nicely. What is LPT rule? So offline situations, so suppose all the tasks are given, then we can use LPT rule. So longest processing time passed. And LPT rule simple, sort the job based on decreasing processing time. Decreasing processing time. So T1 is greater than T2 is greater than Tn. So this is decreasing processing time and schedule based on this. Execute the list scheduling on the sorted list and return the schedule so obtained. And LPT rule is 3x2 approximations, and this is proved in your Eva book. This is section 11 of Eva book, and it is again LPT rule is again 4x3 approximations. This is also given in the Eva book. Okay, both are given in Eva book, but let's see very simplistic 3x2 approximation how can prove, and 4x3 I am leaving you as homework kind of thing. You can see the Eva book, because anyhow what I'm teaching from the book. Okay. So tasks are ordered in sorted order. So can I say, suppose tasks are ordered in sorted order, and first task is highest execution time and last one is the lowest execution time. And suppose J is equal to M plus 1. So M plus 1 job. So M is number of machines. J is greater than M. And can I say T star is greater than equal to 2 into T M plus 1. Suppose there are M plus 1 job. J is M plus 1. Okay. So number of job is equal to M plus 1. Can I say T star is greater than equal to 2 M plus 1? Suppose M is equal to 5 and J is equal to 6. And this is the order. So suppose these are the taxes 10, 9, 8, 7, 5, and 4. And T M plus 1 is 5 machines, 6 taxes. T M plus 1 is 4. Can I say whatever the time produced by or Cmax time produced by any optimal algorithm will be greater than equal to 8? Can I say this? Number of processor is 5. Number of tasks is more than 6. And these are the taxes. Okay. And whatever the optimal algorithm it produces, the result it will be greater than.
Yes, sir.
8. Because this 5 processor is already busy. 5 processor is already busy, and this one is the 6th guy. 6th guy need to be allocated to any one of the machines. That means if you take any of the taxes, it will be, suppose this may be 4, 4, 4 always, but it will be greater than, T star will be greater than equal to 2 into 4. So T star will be greater than equal to 2 into 4. If it is not less, then suppose all are equal, still it will valid. If it is greater, then definitely it will be higher. Okay. So if you go further, then what I'm trying to do, this thing already explained with examples. Okay. So now suppose a machine MI have at least 2 jobs. Okay, and at least 2 jobs, not 1 job, 2 jobs, and TJ is the last job. J is greater than or equal to M plus 1. So earlier it was J is equal to M plus 1. Now I'm saying J is greater than or equal to M plus 1. So J is greater than or equal to M plus 1. Earlier it was M is equal to 5 and J is equal to 6 with 2. But now suppose 7 taxes. Okay, so J is greater than or equal to M plus 1. At least a message MI have at least 2 jobs. Okay, so can I say Tj is less than or equal to Tm plus 1 because J is, if you look at this term, J is greater than or equal to M plus 1. But J, suppose earlier it was 6 trucks, now it is 7. So Tj, because 7 taxes, it will be less than. Tj will be less than Tm plus 1. And this thing, because Tm plus 1 it will be less than or equal to T star by 2, because from this we can get this thing. Okay, so now suppose you have another thing is Tj is less than or equal to T star because optimal value of Cmax, that is T star, will be always greater than execution time of any taxes. This is one. Second one is Ti minus Tj. So what is Ti? Let's define a term Ti. For Ti is the sum of all execution time of tasks assigned to machine I. Suppose let's define a term Ti, and Ti is equal to execution time of tasks. Execution time of tasks. Okay, assigned to machine Mi. Okay, so can I say so Ti minus Tj is less than or equal to T star? What I am saying, all the tasks assigned to this machine Mi minus Tj okay, is less than or equal to T star. So same arguments, up to that point all the machine will be busy. Up to that point all the machine will be busy. So earlier in general list building also we did same thing. Okay, so up to Ti minus Tj time, so all the machine will be busy, and the optimal algorithm will be cannot be less than that. Okay, so that point. So can you recall that thing? Up to Ti minus Tj, all the machines will be busy. So that is the term, and T star cannot be less than that. So that thing we're taking. Okay, if you look at that thing, so Ti minus Tj is less than T star, then it implies Ti is less than equal to T star plus Tj. Okay, so same thing rearranging, and Ti is less than equal to T star plus. Now this Tj, what we are taking? This Tj we are taking from this thing. Tj is less than equal to T star by 2. This thing we are putting. So now this value we are putting here. This Tj value we are taking from this, and we are putting value here. So now Ti is less than equal to Ti star plus T star by 2. So now Ti is less than equal to 3 by 2 T star. So in this way we prove it is 1.5 approximations. Okay, 3 by 2 is 1.5 approximations. If you sort the tasks using LPT order, then you will get 3.5 approximations. And this is very simplistic way. This thing I have taken from exactly from Eva Tato's book. Please go and read the Eva Tato's book, approximation algorithm sections. You will get the proof for this. And if I win it out, please ask me. Hello?
Okay, sir.
So, and for these approximations, 4 by 3 approximations, I am giving you as a homework. Anyhow, you need to go and read from the book. So I am giving you as homework and read the approximations. And now we are moving towards another problem. So what is this problem? The problem is Pj is equal to 1 summation of Wj Uj. What is the meaning? What is the meaning of the problem?
Sir, we have some number of identical processors. The processing time of all the processors are same, and we need to minimize, and also the deadline for all the processes are given,
Yeah.
and we need to minimize the number of processes that completes after deadline.
Yeah. Uh, uh, Formally, what I can define is there are m identical processor and taxes. All execution time are 1. Unit time, execution time. Okay. They have individual deadlines. Preemption is not allowed. Okay. And what we want to optimize is summation of weighted missed job. Summation of weighted missed job. Okay. Summation of weighted missed job. So Wj is weight and Uj means if it is a miss, then only Uj will be 1. Okay. Uj will be 1. So what you can say, Uj is equal to 1 if Fj is greater than Dj. If Fj is greater than Dj. So Fj is greater than Dj, then only, otherwise it will be 0. So Uj is missing 1. So if Uj is equal to 1, that means that tax missed. And what we want to minimize? Minimize the summation of weighted mixed taxes. Okay, weighted missed taxes. Okay, so anyhow, means how we can solve this? This is the problem. We have m processor and taxes. All taxes arrived at time 0. Everyone have execution time 1. Okay, and everyone have deadlines, individual deadlines, and we want to minimize the summation of weighted missed taxes. So approach 1, suppose simply scheduling and rejecting the on-peak taxes will minimize Wi. So that may not happen. Suppose you take taxes 1 by 1 because all taxes have equal execution time. And try to take as many taxes you want, one after another. It may not work. If you take based on simply deadline, you try to get one after another and try to schedule. And if you are not able to do, then reject it. Okay, so it will not minimize the Wi. It will not work. I will need to take care of weight. Suppose you sort based on WIDI, give priority of taxes with higher weight. Okay, so similarly, simply reject the taxes based on deadline because we sort based on the WIDI. So can it work? No. Simple sorting by WIDI also it will not work. So how to solve? Is there any way to do? Hello from student side. How to solve this problem? And what I'm saying is algorithmic volume time algorithmic approaches exist for this problem, and it's not very difficult. Anyone can guess. I want to know from you people what can be the solution approach. Okay, let's see. So the solution approach is we need to take care of deadline. There is no issue. Okay, and then so this is the sort all the taxes based on deadline. So first thing we'll do is sort the taxes based on deadline. Then this is the initially the set. What is the set? It says that what are the accepted tax. So this is the accepted tax. Out of n taxes, which taxes are accepted to schedule? Means they meet the deadline. Okay. So tax are sorted based on the deadline. So initially we'll take the lower deadline taxes. For I is equal to 1 to n. So we'll take one by one all the taxes based on deadline. And what we'll try to do, if the higher tax is late, one schedule in the earliest time slot on the machines. What that means? So because every time whenever we're picking a tax, okay, suppose higher tax means this deadline is D2. Suppose you are picking a second taxes. Whatever the deadline at that time will you look at. So whenever you try to schedule the tax 2, suppose you are taking D2, okay, or tax 2, then if second tax is late, one schedule on the earliest time slot on the machines. Suppose you are not able to schedule the higher tax, then can you replace the older taxes? So that is the idea. If you can replace, then replace it. If you are not able to replace, reject it. So what is the meaning? So meaning is which taxes to replace and how to replace. So find a tax I star, another taxes, which weightage I star with WI star, minimum weight of taxes in the already scheduled taxes of set S. Suppose you have already scheduled 10 taxes and you are considering 11 number taxes, and 11 number taxes deadline is little bit higher as compared to whatever already scheduled 10 taxes. That we know because all the jobs are sorted based on the deadline. Suppose 11 number taxes, you are not able to find a slot within that deadline, D11 timing. If you are not able to do, then what will do? You try to find a taxes already scheduled the 10 taxes, whichever is having lesser weight. Means lesser weight taxes. If lesser weight taxes are getting scheduled and this 11 number taxes have higher weight, then take out the lesser weight taxes and schedule W star is less WI, then replace I star with higher taxes. That means go serially, okay, go serially based on this D1, D2, DN. And whenever you see a taxes, 11 number, for example, 11 number taxes, and we have already scheduled 10 taxes. 11 number taxes you are not able to schedule, and we have scheduled 10 taxes, but among the 10 taxes, some taxes have lesser weight, or one taxes have lesser weight as compared to the 11 number taxes. Then take out that taxes, whichever having lesser weight, whichever one the least one, minimum weight one, so that you can put this 11 number one. Because our main goal is to minimize the summation of WJ. And if you do this process, then definitely you will get optimal result. This is proved to be optimal. Is this clear? Or do you have any questions?
Sir, we are sure that just taking out one task will be enough. Like it might be possible to take arbitrary number of tasks.
No. So whichever the minimum weight taxes we are taking. So in this case, what we are saying is, so WI star is the minimum weight of taxes. Only one taxes, because we want to schedule one after another. Suppose 11 number taxes, suppose you want to schedule, and already 10 taxes already scheduled. We want to schedule 11 number. Out of this 10 taxes, whichever having minimum weight, you take out that. Suppose two have same weight, then you can take out any. But whichever is the minimum weight, and that will give you optimal result. And this is proved to be optimal, and this we can do in n log n time, because sorting job will take order of n log n time. And if you are able to find a slot, just add this task. If you are not able to find the slot, then only you should do. If you are able to find a slot for ith task, then schedule. There is no issue. The only case is if you are not able to find, then replace the already scheduled tasks, which have actually minimum weight, and this will give you the minimal or what I can say optimal result. And this is proved. We can prove also with argument. Is this clear? Any doubt? Okay, so let's move towards another problem. So similar thing, but what is the difference? So this problem is Pj is equal to 1 summation of Wj Uj. What is the current problem? What is the problem? So P M identical processor.
Number of late jobs.
Minimizing number of late job, and execution time is arbitrary. Execution time is arbitrary. Okay, and this problem is very difficult problem. If execution time are arbitrary, then this problem is very difficult problem. So this is NP complete problem, and sorting based on deadline is an excellent heuristics. What do you say? Sorting based on deadline is excellent heuristics for most of the cases, and it is proved experimentally, but not optimal. And you can find the counter example. Suppose there are 3 jobs. Okay, this is processing time and deadline. So J1, J2, and J3. So this have execution time 1, deadline 1, execution time 1, deadline 2, and execution time 3 and deadline 3 on 2 processes. Suppose you sort the job based on end deadline first. Okay, so earliest deadline first. Okay, earliest deadline first, EDF way. So sort based on deadline. So if you sort based on deadline, which tasks will schedule first? So J1, J2, and J3. So based on this order, we will schedule. So J1 got scheduled, J3 got scheduled. Now, once J1 and J3 got scheduled on 2 machines, machine 1 and machine 2, J3 tasks will miss the deadline. Will not get options to schedule on any of the machines. It will miss the deadline. J3 will miss the deadline on both the machines. Even if schedule on machine 1 or machine 2, both the machines, it will miss the deadline. But optimal is this one. So if you schedule the J1 first on machine 1 and J2 on machine 2, and both will meet the deadline. These are the deadline. So this is D1, D2, and D3. So what is D1 is 1, D2 is 2, and this is 3.3, 3.5. So
sir, if
D1, D2, and this is D3. This is 1, 2, and 3.5. Yeah, please tell.
Sir, if we sort on the basis of DJ minus PJ, then it would work.
No, it will not work. You may find counter example. So any kind of thing will not work. It is proved to be NP complete. That's why I'm telling. So this is proved to be NP complete. So we should not try this thing. But EDF definitely it will not work. We have counter example, and we may find counter example for that also. For simple EDF, we can find out counter example very easily. So what I'm trying to say is this problem is a really very difficult problem. So you have M processor, and all the tasks have arbitrary deadline, and we want to minimize the late job. Minimize the late job without wait. Minimize the late job. Then this problem is really difficult problem. Okay, but EDF actually gave very good, nice result experimentally. For most of the cases, it gave very nice heuristic. So in my research also, many papers we use EDF means particularly sort based on deadline, and it worked very nicely, but it is not optimal, not proved to be optimal, and it is heuristic. We are not able to prove the approximation bound also. No one is able to prove. So this is the status. Okay, so let's move towards another one. So can I say with preemptions it is solvable? Suppose you allow preemptions. With preemption it is also it's very difficult problem. Okay. So with preemptions, if you allow preemptions also, then also it is very difficult problem. Okay. So now moves towards another problem. So that is Q, PMTN and CJ. What is the problem? Can someone says what is the problem? Q, PMCN and summation of CJ. What is the problem statement? Hello? Hello?
Uniform processors, preemption is allowed, and we have to minimize the sum of completion time.
Completion time. If suppose all the tasks arrived at time 0, it is same as average waiting time. Minimizing average waiting time. Same as minimizing average waiting time. Okay, summation of completion time. Suppose you want to minimize this summation of completion time. So this problem is also actually polynomially solvable. This is a very interesting problem. Okay, and many what you can say system they use this approach to solve the problem. Okay, so many time we have actually uniform processor many system, and we want to minimize the actually waiting time. They use this approach. Okay, so what is the approach? LPT on high speed is good to optimize summation of EI, sum of all execution time, but not the summation of CJ. Okay, so summation of completion time, LPT on high speed, but modified version time rule it will work. So modified version of SPD. So earlier also we did the same thing, Q, PTMN and what CMAX, Q, PTM and CMAX. So exactly same approach. So in that case, so whenever two guys meets the joint point, then they co-schedule. So in this case, it is a little bit different, but similar. Concept is similar. Okay. So out of the tasks based on the non-decreasing processing time, schedule task 1 on available highest speed machines up to T1 by P1 by S, then schedule second machines. Okay. Second machines on this up to means T2 and greater than until this complete the and same process continues. Okay. So here also this co-executes and this thing will not work, but directly whenever one is overtaking, then give to the another one. So shortest remaining time. So highest shortest remaining time on high speed processor, and that will give you the optimal result. So what is the approach? Shortest remaining time on high speed processor. That is proved to be optimal. So these are the 6-7 things I wanted to tell in this courses before starting up the cloud things. Okay, so next week or next after the mid semester, so we'll have actually started a new topic, cloud and IoT and this thing. But this scheduling concepts need to be used in that part. Okay. So this is done. So today we finished at right time all the things. Do you have any questions?
Sir, in this case, P1 has the highest time, so P1 should have gone first.
No. P1 is gone first because this one is we're giving to first machines. Let's see. So machine is 3. So maybe first one is high speed machines. P1 is gone first, but thing is that once this remaining time is lesser than other job, then it depends upon the remaining time. So here SRT job J4, if you look at this thing is shortest remaining time. So what we are trying to do is shortest remaining time. What we are trying to do is we start with shortest remaining time. If you start with the J1, then it will increase your CJ. Are you getting a point?
Yes, sir.
If you start with J1, then it will actually increase your CJ. Completion time will increase because we need to overall we need to reduce the overall completion time, just like SPT. Shortest job first or preemptive shortest first job. What it do? Overall, if you minimize the summation of CJ or minimize the average waiting time, we try to first give to shortest remaining time. So that's why we're giving shortest remaining time first. Whichever is shorter, we're giving to the high speed one, so that overall summations will be reduced. And preemption is allowed whenever it is shorter, then it will switch. You got my point?
Yes, sir.
Okay, so okay, look at in this case, so J1. So J1 were given to the least scheduled machines, but once this J2 got finished, it moved to another machines. J1 got moved to another machines. Again, in this case, J2 finished, again this J1 got moved to the high speed machines. So J1 is moving from low speed to high speed machines. Here J2 is moving from low speed to high speed machines. J3 is moving from low speed machine to high speed machines. And J4, anyway, it is shorter one, it is in the high speed machine. Are you able to see this thing?
Yes, sir.
So J4, then J3 is moving, J2 is moving from lower to high speed machines, J1 also moving from higher to lower speed, lower to higher speed machines. And it is preemption is allowed. Okay, preemption is allowed means migration is also allowed. Okay. Okay, thank you. So these are the some status of the what are the scheduling problems, and we'll use these scheduling problems in our course.
Sir, in midsem, is the initial part serial code optimization those included or after the quiz or everything?
No, mid semester will have two 30-minute questions, and one will cover post quiz 1 to mid semester, and second one will have actually full coverage from lecture 1 to lecture 19 all.
Okay, thank you, sir.
Okay, I'll inform you. So in MS team, I'll inform you this thing.